I hope the screen is visible, right? Okay. Welcome to the problem solving session for the week 4 of the course Geotechnical Engineering 1. I am Yogendra Narayanan. I am a PMRF research scholar and the course instructor uh, for Geotechnical Engineering 1 for mm, is Professor D.N. Singh from IIT Bombay. So the purpose of these sessions is to make the learners proficient with the concepts that has been covered in a particular week by solving some problems uh, and uh, and simultaneously clearing the concepts so that it will be helpful for them in their future endeavors, whether it is NPTEL exams or any other competitive exams or further uh, in their further professional journey. So with this, uh, the week 4 content was briefly on some of the terminologies that fundamental terminologies used in soil mechanics and how they are related and how uh, to an extent the learners have been introduced to some of the basic testing of index properties, and based on those concepts covered, we will be solving some problems today and some questions, some conceptual questions also. So with this, we'll get into the session. So first question, which among the following has minimum specific gravity? Question 1 is, which among the following has minimum specific gravity? Option A, bentonite. Option B, quartz. Option C, peat. And option D, clays.
I think peat.
Okay. So when we consider the other options, bentonite is its specific gravity ranges from 2.4, and quartz ideally its specific gravity is 2.65, and as far as clays are considered, the typical values is 2.7 to 2.8. And peat is typically the range around 2, maybe 1.7 to 2. So you can always find that soil with organic matter tends to have a lesser specific gravity. So that is how the presence of organic matter in a soil is speculated, and further it is being quantified. So these are the typical specific gravity ranges, and among this, any soil with maximum organic content, and peat is completely organic, so it has a very less specific gravity, and so the answer is peat. Right? So any doubts or any clarification?
Sir, can you little zoom, sir?
Yeah, okay. I hope
Okay, sir.
now it is
Okay, sir.
pro-
Okay, sir.
right.
Yeah, that's okay, sir.
Yeah. So coming to the next question, which is the correct relationship between Voigt's ratio and porosity? So which is the correct relationship between Voigt's ratio and porosity? Which of the following?
Option B, I think.
Option B.
Yeah.
Okay. So let us derive
Option
this.
A, sir.
Yeah. So for understanding, we can derive this. Porosity is defined as volume of voids by total volume, right? And E is defined as volume of voids by volume of solids, right? So if you take this volume of voids or if you take this volume of voids by V can be written as volume of voids plus volume of solids, right? Now you can cancel, you take the V common, volume of voids common, you get 1 by 1 plus Vs by Vv. So now this is, if you take both side out, it will get cancelled, and now it is 1 by 1 plus 1 by E. So eventually it will give E by 1 plus E. So porosity is defined like porosity is White's ratio by 1 plus E. So what is the term called 1 plus E? Any idea?
Specific volume.
Yeah. So specific 1 plus E is known as specific volume. So you can, what is the significance of specific volume is that it is a normalizing term. It can be treated as a constant term. So here, when if you take the phase diagram, it contains volume of or contains volume of solids plus volume of voids. So so this is solids voids. Now its volume is Vv and its volume is Vs. Now you know that when now we consider Vs is 1. Let Vs is equal to 1. In that case, the total volume will be 1 plus, what will be the uh, volume of voids in this case? It will be E, right? So E is volume of voids by volume of solids. So volume of solids is 1, so it is equal to Vv. So when we consider a system where the volume of solids is 1 or unity, so the volume of voids will be equal to its void ratio, and the total volume will be 1 plus E. Now if you take this, so porosity is nothing but for a unit volume of uh, solids, so it is ideally total volume by volume of voids. So if you take this ideal condition, E is volume of voids, total volume is 1 plus E. So this is one another way of deriving it. Any doubt?
Okay, sir.
Uh, I hope it is clear. So we can move to the next question. So in which type of soil does core cutter method is preferred? In which type of soil does core cutter method is preferred? Option A, cohesionless soil. Option B, cohesive soil. Option C, both cohesionless and cohesive soils. Option D, none of the above. In which type of soil is core cutter method preferred?
I think both cohesionless and cohesive.
How does core cutter method work? Any idea? How do you do core cutting? Core cutting is usually done by using uh, it is kind of a sampler, or you could call it is its exact term is core cutter, which has a by which it is placed on the ground and it is driven into the ground. Of the core cutter has a known volume and it is driven into the ground, and after it is driven it is taken out and the entire plug is weighed and we know the total volume, and corresponding volume is calculated, and we get the density as uh, which is considered to be representative of the ground. So when you take the core that is cut, uh, so the primary condition is that the plug that you retrieve should be intact. So in case of sands, whether it will be intact or it will not be. Can you cut the core out of sands? So you cannot cut the core out of sands. So that's why you will not get the proper. So core cutting is not advisable for cohesionless soil. It is usually done for cohesive soil. And what is the other method? The other method is sand replacement method, which are these are conventional methods. Sand replacement method. So sand replacement method is used for both cohesive soils as well as cohesionless soils. So both are applicable for sand replacement method. Now modern techniques such as nuclear density and uh, several other non-invasive techniques have also been introduced into the measurement of the density. So, but as far as conventional methods are considered for field density measurement, uh, we use sand replacement and core cutting. Any doubts? The person who has joined from recently can follow from the next question or from this question. So, any doubts with the explanation?
It's fine, sir.
Okay. So you are free to interrupt whenever you have a confusion or uh, or you have you need anything to get anything to be clarified, you are free to interrupt. So moving to the next question. So the Void's ratio of a sand is 0.7. What would be the relative density of it if the minimum and maximum Void's ratio are 0.55 and 0.90 respectively? The Void's ratio of a particular sand is 0.70 at a particular condition. What would be the relative density of it if the minimum and maximum Void's ratio are 0.55 and 0.90 respectively?
Sir, move up, sir. Fourth option not visible.
Ah,
Yeah.
now what is the relationship for relative density? dr is equal to E max minus E divided by E max minus E min, right? So we know this is E minimum, this is E maximum, and this is E at the present state. This E corresponds to the present compaction state. So E max is 0.9, E is 0.7, then E max is 0.9 minus E min is 0.55. So what is the value we are getting? Please compute and let me know.
Point 5714.
Okay. So we get 0.5714. In percentages, it is 57.14%, and it can be rounded up according to the option it as 57%. So any idea how E max and E min are determined? So the right option is option A. How E max and E min are determined?
By
How
vibrating,
the
by
samples are
vibrating
made?
a sand, vibrating a sand in laboratory with weight and without weight.
So that gives you E.
E max and minimum. With weight, you will get E minimum. E minimum. Without
Yeah,
weight, you get an E max.
yeah. So mostly the placing of sample is done by air fluviation technique, and then it is vibrated. So at the densest state, it will have its minimum Void's ratio, and its loosest state corresponds to its maximum Void's ratio. Hope it is clear now, right? Yeah, people tend to get confused. E max corresponds to the loosest state and E min corresponds to the densest state. Please do not get confused here. Now moving to the fifth question. A soil in its compacted state has the following properties: porosity of 0.375, degree of saturation 0.90, specific gravity of 2.65. What is the water content of the soil? The soil sample is being considered, which is prepared with the porosity of 37.5%, or in decimal it is 0.375, degree of saturation of 0.9, and specific gravity of 2.65. What is the gravimetric water content here? How do you get water content? So the basic governing relationship is saturation into White's ratio is equal to water content multiplied by the specific gravity of soil solids, right? So you need E. First, the unknown is W. W can be written as S or S, any notation is fine, by GS. So now you know the saturation, you know the specific gravity. E you need to derive. So we know that porosity is equal to E by 1 plus E. So now if you have 0.375 plus 0.375 E is equal to E, right? How much is the White's ratio we are getting? Please compute and let me know.
0.6.
Is 0.6. Now if you substitute in this, water content will be 0.9 into 0.6 divided by 2.65. So how much is the water content? How much is the water content?
$20.37.
This comes around 20.37%, which can be rounded up to 20%. 20% will be the answer. Any doubts? Any confusions? So as far as this part is concerned, who are joining new or whoever is uh, freshly introduced to geotechnical engineering 1, so the you can expect several different types of questions with the basic weight and volume relations itself. So it is better to get complete clarity of what each term means and how it is related. So if you are confused, you can go from the first principles, from the basic definition of these uh, of these uh, parameters so that you can understand it better. Or the fundamental way would be approaching it from the phase diagrams. Hope it is clear now. Moving to the next question. So it is a continuation of the previous question. So we have derived the water content. So now for the particular existing state, what is the dry density? At what dry density this particular sample of sand exists for the given saturation and what saturation condition. So how do you calculate dry density? What is the relation for dry density? So dry density is gamma W Gs by 1 plus E. So now you can calculate in gram per cc. Since it is in gram per cc, gamma W is 1 gram per cc, 2.65, and 1 plus 0.6, 2.65 by 1.6. How much it is coming?
1.656.
It comes to 1.656, which can be rounded off to 1.66 gram per cc. Alright. So the answer will be this one. Now moving to the next question, seventh question. Among the given options of particle sizes, where does silt fall? What is the silt size ideally? Not ideally, among the given sizes. The options are in millimeters. So if you are finding it confused, you can convert it into microns also, or you can do it from mm also. So the gravel will be greater than 4.75 mm, and sands will be 4.75 mm to 75 microns, and silt size will be 75 microns to 2 microns, and clay sized particles will be less than 2 microns. So here if you convert it, it will come to 70 microns, and this will be 2 microns. So the ideal silt size is 2 microns to 70 microns among the given ranges. So the suitable answer is option C. Here the important thing is these are classifications purely based on sizes. So you should not get you should not get confused with the actual uh, the term clay here specifies the clay sized fraction. So it does not necessarily be clay. Silt sized fraction, sand sized fraction, and gravel sized fraction. So further classification of whether it is a clay soil or silty soil is done by further index testing, which we'll be studying in the next week, which is Atterbuck's limits and that is uh, plasticity limits, consistency limits. So based on that, you will be studying, and the type of clay can be determined by using several techniques uh, to determine the mineralogy as well as the chemical composition by using XRD, etc. Any doubts?
Sir,
Yeah.
sir, silt material as alone, not mixture.
Mm-hmm.
Uh, where we can use and where we can avoid.
Silt, uh, here as a silt refers to the how to put it. So it is a here it is silt sized material. So wherever so even though they are non-plastic, they are highly since their sizes are small, so their permeability is very less. So um, usually silts are as such uh, it is kind of an intermediate material. So uh, it,
Is it a good filler in compaction?
to an extent, yes, higher particle, uh, but since its permeability is very less, so the pore pressure buildup will be high. So its dissipation of pore pressure will be low. So it is not as such suitable for backfilling also. So
Yes,
if
sir.
we, yeah,
Normally, silt which is available in the sea coast is a salted one. We don't use it.
yeah.
But the
So that
silt
is
which may
due
be
to
available,
its it is very sensitive. So when you disturb it, it will its entire strength will it will
collapse.
the salt will leach out and its entire structure will collapse.
Yes, sir. It's only by like a mixed design we can mix it and we can use it, or alone we can use anywhere.
To an extent, you can use it in filters by mixing it
Other-
with a particular proportion to with sand. You can mix it at several layer of filters. So that will be as such silt is intermediate material. So uh, pure silts are not used as such.
Okay, okay. For example, in a Loess material, where
Yeah.
naturally wherever it is available,
Mhm.
it's difficult to construct any infrastructure, no, sir,
Yeah.
over
So that is lowest will be a very loose deposit,
a loose deposit, but it is a silt
silty
particles also.
material. Yes.
Yeah. Okay, okay, okay. Right, sir. Done.
Yeah. So now moving to the next question. So why H2O2? That is hydrogen peroxide. is added to soil before performing hydrometer analysis. Why hydrogen peroxide is added to soil before performing hydrometer analysis? To prevent clogging of soil particles, as a dispersion agent, to remove the organic content, or it is none of the above? Any idea? So this H2O2 hydrogen peroxide is usually to remove organic content. Why it is used to remove an organic content? What property of it is suitable to remove the organic content? Any explanations?
Will it oxidize the organic matter, sir?
Yeah. So hydrogen peroxide is a very strong oxidizing agent. So which you might have come across in your 12th standard chemistry. So it is a very strong oxidizing agent which will oxidize the organic matter that is present. And initially, as a double check, we usually it is also organic content can be removed by to an extent by uh, heating in the oven, keeping in the oven at 100 to 105 degrees centigrade. So to an extent it can be removed, but by adding chemicals, one of the best agents is any oxidizing agents can be used, and most commonly used oxidizing agent is hydrogen peroxide. So the right option is option C. And in order to quantify the organic content, usually the entire sample is heated at 440 degrees centigrade in a muffle furnace for 2 hours, and then uh, it is the weight loss is uh, determined, and that weight loss is corresponds to the loss in organic matter. Any doubt? So the right option is to remove the organic matter, organic content in the soil. So coming to the next question.
Sir, excuse me, sir.
Yeah,
In the hydrometer analysis,
yeah.
uh, I think maybe in your research laboratory you are using some recent modern equipment. Is it still hydrometer analysis is popular, or any other is replacing the hydrometer?
For particle size distribution, there are many new techniques that are coming. So there are uh, laser imaging and stuff like that. So those techniques are more advanced, but ideally for our simple applications and simple characterization of soils, it is still uh, uh, this hydrometer analysis. In for commercial or for regular characterization purposes, we use hydrometer analysis.
Okay, sir.
Uh, but now several uh, advanced techniques have come for particle size analysis, so that is also being used. There are scanning equipments, laser scanning, and uh, usually now one of the advanced equipment is laser scanning and laser imaging. So coming to the next question, which among the following statement is incorrect? So which among the following statement is incorrect? Meniscus correction is always positive. Temperature correction is negative when the soil solution temperature is below the calibrated temperature of hydrometer. Dispersion agent correction is always positive, both A and B. Which among the following statement is incorrect? Meniscus correction is always positive. Temperature correction is negative when the soil solution temperature is below the calibrated temperature. Dispersion agent correction is always positive, both A and B. Any guesses or any answers? So now to understand, to approach this, we need to understand the several corrections, right? So I will give a brief account of what are all the corrections that are how the corrections are calculated and uh, actually happens and why these corrections are required. So now we consider a slurry which we have prepared for in order to do the hydrometer analysis. So and we are filling it. Consider this: we are filling it with uh, the soil slurry which we have diluted it to 1 liter in a measuring flask, and you insert hydrometer, right? So hydrometer has a bulge in which glass beads are filled. So if you enlarge it, the ideal demarcation in hydrometers will be like this, which will start at 0.995, 1.000, 1.005, 1.010, and it goes on up to 1.030. So this is a typical demarcation which is present in the stem of the hydrometer. All right. Now, when you insert it, what happens is that uh, so when we enlarge the column here, so you are inserting it, right? So what happens is that consider there is a demarcation here and a demarcation here. Okay. So let it be 1 and let it be 1, let it be the next demarcation which is 1.005. What happens is that when you place the hydrometer inside the solution, due to the surface tension, there will be a meniscus that is formed. So this meniscus will always be on upper side to the actual water level, or not water level here, the actual the soil solution level. So whatever the reading you take will be, you will be able to see this demarcation. So what you will do is you will note it down wrongly as 1.000 at a particular time. but the actual correction is this one. So usually it is when during its calibration, so we always check the uh, meniscus correction. So usually this meniscus correction, since its demarcation is in the positive demarcation increases with in downward direction, so we will always add the correction to the actual values. Let it be 0.005, a simple example, and the correction will be always positive in case of meniscus correction. So this statement is right. So now coming to the next point, temperature correction is negative when the soil solution temperature is below the calibrated temperature of hydrometer. So when the temperature is more, water tends to expand, or there will be, and also corresponding density changes will be there. So in that case, the entire hydrometer is calibrated at a particular temperature, and when the temperature is low, let it be this is the calibrated temperature, and when the temperature this is the water level at a particular calibrated temperature. Now let it be 30 degrees. Now when the temperature is lesser, the water level tends to be relatively minimal, to a minimal extent it will tend to be lower. So let it be you are testing at 20 degrees centigrade. uh, your your present testing temperature is 20 degrees centigrade, so your water level will be lesser. So in order to correct the value corresponding to 30 degrees centigrade for which you have calibrated the hydrometer, so you need to bring the value from here to here, for which you need to subtract it. So that is why when the soil solution temperature is below the calibrated temperature, where this is the case, you will have to subtract the values for which the temperature correction is negative. And in case if you conduct a test at 35 degrees centigrade, what will happen is that the water level will be somewhere here. So in order to normalize it, you need to correct the temperature by adding it. So that is why when the temperature is higher than the calibrated temperature, the correction is always positive. When the temperature is lesser than the calibrated temperature, the correction is always negative. So the third option is also, second option is also right. Now coming to the dispersive agent correction. So due to the addition of dispersion agent, the density of the water tends to increase. So due to which there will be a rise in or the due to the dense increase in density from actual water level, there will be a slight decrease in water level. So that is why in order to correct it for that, we need to subtract the difference. So dispersion agent correction is always negative. So this option is incorrect. So our answer will be C. Dispersion agent correction is always positive, which is not the case. Any doubts? So it might be slightly confusing. If you are not, if you want me to explain once again, I can explain it. Or to what extent do you were able to follow? Okay. So I hope the explanation is clear. And if you have any doubts, you can ask. And coming to the next question. if the soil particle diameter decreases by a factor of 2, what will happen to the settling velocity? If soil particle diameter decreases by a factor of 2, what will happen to the settling velocity? Uh, Now we need to understand what is the relationship between the particle size and particle diameter and settling velocity. So as far as Stokes law is considered, settling velocity is directly proportional to square of the diameter of the particle of any particle. So when now let us consider initial for diameter d1, velocity is v1. So v1 by d1 square is equal to v2 by d2 square. All right. So now d2 is half of d1, that is d1 by 2. Now same relation, d1 square is equal to v2 by d1 square by 4. Now moving this, v1 is equal to 4 v2. So we need v2. v2 is v1 by 4. So when you decrease it by 2, the velocity decreases by 4 times. So the option is D. Any doubts? Any doubts?
No, sir.
So just a minute, I will be back in a minute. So sorry for the inconvenience. I will be just back in a minute. So we will move to the next question. So what is the relationship between sphericity, roundness, and rigidity? So what is the relationship between sphericity, roundness, and rigidity? Any guesses? So usually rigidity is related by sphericity plus roundness factor, average of these two. So these are essentially empirical relationships, so which has been developed. So the option will be first option, which is S plus R by 2. Okay. So come, any doubts? So coming to the next question, the air content of a soil mass at complete saturation is. Air content of a soil mass at complete saturation is. So as the complete saturation means all the voids are completely filled with water. So there is no place for air to exist. So if we think logically, the air content should be ideally zero for any soil with at 100% saturation. Complete saturation is 100%. All right. So moving to the next question. So the dry unit weight of a soil fill is found to be 15.8 kilonewton per meter cube. The specific gravity of the soil solids is 2.65. The maximum and minimum voids ratios determined in the laboratory are 0.88 and 0.42 respectively. The relative density of the soil is. So we have been given the dry density, which is 15.8 kilonewton per meter cube. We have been given specific gravity, which is 2.65.
What is gamma W, sir?
Gamma W, you can take it as 10, or it is better, it is not specified, so you can consider it as 9.8, 9.81. You work it out so that we can check the values which are coinciding. So gamma W is 9.81, and values which we have, other values are E max, which we have 0.88, E min is 0.42. These are the details we have. So what we want to find is relative density. So relative density is written as E max minus E minus E minimum. Now we know E max and E min, we need E. Now how can we find E? For that we know dry density is defined as gamma W C by 1 plus E. So for finding E, substitute gamma W 9.81, GS 2.65, gamma D is 15.8. Now if you take this entirely minus 1, how much we are getting?
0.645.
0.645. Now substitute here 0.88 minus 0.645 divided by 0.88 minus 0.42. How much we are getting?
0.5, 51%.
So you will be getting around 0.51, this approximately 51%, equal to 51%, which is relatively coinciding with the answer of the option D, 52%. So this minor variation is due to the values of uh, water, unit weight of water. So if you use 10 and if you use 9.81, these fluctuations are bound to occur. So it should not give drastically erratic results, but this 1 or 2% is fine, right? Any doubts? Person who has joined recently, you can also you are also expected to solve the problems and get your doubts clarified. Any doubts?
No, sir.
Now moving to the next question. A soil sample is found to have a porosity of 0.25 of the specific gravity of 2.65 and water content of 15%. Can a soil sample exist in this state? How will you determine whether the soil sample can exist in this given state or not? How can we approach this problem? Any idea?
I think degree of saturation should be within the limits. Should not be out of the boundary.
So whatever first the parameters which we have is porosity, specific gravity, and water content. So if you have porosity, you are indirectly having White's ratio. So all three, and one more thing left in this group is water saturation. So we know that the saturation limit of the limit of saturation is 100%. It should not exceed 100%, right? So in order to check it, so SR should be less than or equal to 100%. This is the condition, right? Now to check that condition, we need to compute E first. So 0.25 equal to E by 1 plus E, which is 0.25 plus 0.25 E equal to E, which you will get E is 1 by 3, right? You will get 33, 0.33.
Yes, sir.
Right. So which will be 0.33. Now we know the relationship SE is equal to WG. Now S you need to find. W is 0.15, GS is 2.65, and E is 0.33. So what is the degree of saturation you are getting?
119.25.
Yes, you are getting 1.1925.
No, sir. 119.2.
That is percentage, right?
Yeah, that's percentage.
So in decimal you will get 1.19
1.9.
approximately.
Yes.
So that is 119 percentage, which is greater than 100 percentage, right? So this type of soil sample cannot be prepared and it cannot exist. All right. So moving to the next. I hope it is clear. Any confusions? Can move to the next question. The density and water content of a soil specimen retrieved from a field are 18.4 kilonewton per meter cube and 8% respectively. The maximum and minimum dry density is 20 kilonewton per meter cube and 16 kilonewton per meter cube respectively. First thing we need to find is what is the dry density of the soil mass. What is the dry density of the soil mass which was retrieved from the field? The initial dry density, not initial, that actual dry density of that soil for that particular compaction state. So let us solve the first question first. So here the density is bulk density. All right. So we know gamma bulk is 18.4 kilonewton per meter cube and water content is 8%, which is 0.08, right? Now if you write the relationship, gamma bulk is equal to gamma W G S plus WGS by 1 plus okay. So this, so gamma D can be written as gamma bulk by 1 plus water content, right?
Yes, sir.
So,
Yes, sir.
now your gamma bulk is 18.4 divided by 1 plus 0.08. How much we are getting? 18.4 by 1.08.
17.03.
So dry density is 17.03 kilonewton per meter cube. How can we check whether our answer is right or wrong?
It should be between the maximum and minimum densities.
Yeah. So one of the simple way of cross checking is where you should check whether it is in the range of 16 to 20, whether it lies in between. So if you are getting lesser values, then it is wrong. If you are getting more values, you are making some mistakes in calculation. So in terms of the second question is, what is the relative density? So the relative density is in terms of dry density can be, how can we write? 1 by gamma d minimum minus 1 by actual gamma d divided by 1 by gamma d minimum minus 1 by gamma d maximum. Now if you relate it with this, so this corresponds to E max. So when E Void's ratio is maximum, the density tends to be minimum, and when the Void's ratio tends to be minimum, the dry density tends to be maximum. So that is what it is getting reflected here. All right. So now if you substitute the values, 1 by 16 by minus 1 by 17.03 divided by 1 by 16 minus 1 by 18. How much you are getting?
30.24. 30.24.
You will get approximately 30% or exactly 30.24 percentage. Then round it up to 30%. Any doubts?
Sir,
Yeah.
is it only for natural granular materials we can do, or even for rock, floor, or stone dust also we can use it?
Yeah, if it is cohesionless material, we can use it.
Okay, even artificial also.
Yeah.
Okay, sir.
For fine grain materials, it is not suitable. For granular
Yeah.
materials, it can be used.
Yes, sir. Right.
Cohesionless and granular materials. Now, moving to the next question. The Voigt's ratio of a soil sample is 0.35. What will be its specific volume? So it is a fairly straightforward question. The Voigt's ratio of a soil sample is 0.35. What will be its specific volume? So specific volume is defined as 1 plus E, for which the explanation I have already explained. So for a unit volume of solids, the total volume will be 1 plus E. So if the voids ratio is 0.35, it will be 0.35, which is 1.35 specific volume, V specific. So the option is 1.35. Hope it is clear. Coming to the next question. Assuming the shape of grains to be spherical, the voids ratio corresponding to the loosest state would be. Assuming the shape of grains to be spherical, the voids ratio corresponding to the loosest state would be. Option A 0.34, option B 0.97, option C 0.91, option D 0.25. Any answers? So how can we determine voids ratio in this case? So for that we need to consider a particular cube of spherical grain. So let us consider a cube, and the loosest state would be which arrangement? So there are 2-3 types of arrangements. So one arrangement is this is one of the arrangement which is known as cubical arrangement. So in this particular arrangement, the arrangement of grains tends to be at their loosest state. So if we consider in a 3-dimension, so it consists of for a particular element consists of 8 cubes, 8 spheres, 8 spheres, 1 cube. Let the diameter of each cube be d. Right. Now, how we will define the voids ratio? E is defined as volume of voids by volume of solids. Right. So volume of voids can be written as total volume minus volume of solids by volume of solids. Right. So total volume will be how much? Consider this will be the entire side of cube. If this is d, it is 2d. Right. The total volume will be 2d whole cube. This will give 8d cube. So total volume we have found out. Now the next thing we need to find is volume of solids. So solids total we have 8 spheres, and each sphere volume is volume so volume of each sphere is 4 by 3 pi d by 2 cube, right? So, and total we have 8. This is small v 8 into 4 by 3 pi d cube by 8. So you can cancel this. Now, if we substitute v and vs in this equation, so E will be 8d cube minus 4 by 3 pi d cube divided by 4 by 3 pi d cube. So d cube everything can be cancelled. So it will give you 24 minus 4 pi divided by 4 pi. 3 will get cancelled. So if you take 4 pi common, E will be 6 by pi minus 1. How much you will be getting? You will be getting approximately 0.91. So that is 0.91. Any doubts? Is it clear? Is it clear or not? Or you have any confusions? Yes. I hope it is clear. So moving to the next question. So match the type of soil with their maximum particle sizes. Match the type of soil with their maximum particle sizes. So it is a fairly straightforward one. So clay will be 2 microns, silt will be 75 microns, sand will be 4.75 microns, gravel will be 75 mm. So clay will be 2 micron. So these are maximum particle sizes. So this is the upper limit. So 2 microns is for clay, that is lesser than 2 microns are classified as clay. Silt less than 75 microns and 2 microns are classified as silt. Between 75 microns and 4.75 mm are classified as sand. 4.75 to 75 mm are classified as gravel. Hope it is clear. Now coming to the next question. Assign the correct type of gradations to the corresponding figures. Assign correct type of gradations to the corresponding figures. So gradation in the sense, what are different type of gradation? Yeah. Sorry. Sorry. I was there is a small network issue. Am I audible now?
Yes, sir. Audible.
Ah. So I will be sharing the screen now. So till where you have been listening?
Regarding the loosey states maximum white ratio,
Okay. So last, okay.
matching.
Match is done, right?
Uh, Matching, it is not visible, sir, actually, when you make marking.
Okay. Mhm. But that previous question is clear, right?
Yes, sir, it's clear.
Uh,
18th question is,
uh, are you able to see the 18th question?
yes, sir, now I can see.
Uh, so the type of soil with the maximum particle sizes, clay is 75 microns, silt is 2 microns, sand is 4.75 mm, and gravel is 75 mm. So clay corresponds to size less than 2 microns, silt is between 2 microns to 75 microns, sand size is between 75 microns to 4.75 mm, and gravel sizes between 4.75 mm to 75 mm, right?
Yes, sir.
Yeah. So coming to the next question. So assign the correct type of gradations to the corresponding figures. So the three figures shows a typical or a schematic of particle size distribution curves. So based on the given figures, how will you classify the gradation of the soil for corresponding to each figure? So what about first figure? What about second figure?
Gap graded, sir.
Third figure? First one is,
Gap graded soils.
so these are gap graded. Second is
Uniform.
uniformly graded. Uniform or poorly graded. From or poor. Third is well graded sands.
Well graded soils.
Now, if you see carefully this curve, so here there is a dip and all percentage finer are flatter, and here there is a dip. So this corresponds to uh, a particular portion where there is a lot of the
Excuse me.
sudden decrease in the amount of particle that is passing, right? So
Can I
this
interact, sir?
this step corresponds. Yeah, what you are saying? Yeah, please tell me.
And the third graph is showing a little bit more two flat portions.
Mm-hmm.
That is a normally characteristics of the gap graded soil. It should not be that much line. Liner flat portion, you can show it.
Yeah, so the notion for it is to depict a clearly S graph, right? So S graph typically represents a well-graded
Yes, sir.
sand. So maybe it is some drawing issues which was done in hand.
Some source.
Yeah. So
Yeah. Okay,
but
sir.
the notion is to differentiate all the gradings. So thank you for pointing
Hmm.
out. So we will correct it in the further. session.
Yes, sir. Done, sir. Done, sir.
Okay. So here there is a
Clear,
large
sir.
dip which corresponds to a, uniform size of particle, and here relatively there is a wide range of spectrum of particles. So when there is a wide spectrum of particles, so the voids created by the arrangement of larger particles will be filled by smaller particles. So that is why it is known as well graded. In case of uniform or poorly graded, the entire, for example, a sample of soil is consisting of a size of uh, uh, a particular size. So the void's volume will be relatively higher. So that is why it is known as uniform in case of size, and it is poorly graded in terms of its arrangement. And gap graded is, there will be some uh, particular size will not be present, or a particular size will be present, or essentially it will not be present. Gap graded is a particular size will not be present. So that is why there is a dip here. So it corresponds to gap graded soil. Any doubts?
No, sir.
So moving to the next question. A sieve analysis on a sand sample was conducted, and D60, D30 and D10 were determined to be 0.8 mm, 0.4 mm and 0.1 mm respectively. The coefficient of uniformity and coefficient of curvature respectively are. So D60 is given is 0.8 mm. D30 is given 0.4 mm. Is it visible? Is my screen visible and the writings visible? Hello? Am I audible?
Screen is visible. D60 is visible. D30 also now okay.
Yeah.
D10 yet to be written.
D10 I did not write yet. So,
Yeah, it's clear. It's okay.
so D10 is 0.1
Point one.
mm, right? So coefficient of uniformity is defined as D60 by D10, and CC is coefficient of curvature is written as D30 square by D60 into D10, which is, now if we calculate it, D60 by D10 is 0.8 by 1.1, which is 8. CC is 0.4 into 0.4 divided by 0.8 into 0.1. So it can be written as 16 by 8, which is 2. 8 and 2. So Cu is 8 and Cc is 2. Right? So any confusions? I think it is fairly straightforward. So there should not be any issues in this. So direct value substitution. Right. So moving to the next question. Hydrometer analysis is based on the principle of option A Bragg's law, option B Coulomb's law, option C Stokes law, and option D Ohm's law. Which principle governs the hydrometer analysis? So Bragg's law is for, essentially our application is for XRD. So it is mineralogical analysis. Coulomb's law is for electrostatics. Ohm's law is current electricity. Stokes law relates the velocity of a, ideally it is a sphere falling through a water column. So that is related to Stokes law. So it's ideally the Stokes law for our application will be V is equal to gamma solids minus gamma W divided by 18 into mu into d square. Mu is dynamic viscosity. Gamma S is unit weight of soil solids. Gamma W is unit weight of water, and B is diameter. Diameter of the particle. Right. So based on this, we have solved earlier a numerical on it. So here ideally V is directly proportional to d square. This is what our application of Coulomb Stokes law is regarding hydrometer analysis. So the option is C. So moving to the next question. Which of the following chemicals are used as dispersive agents for hydrometer analysis? Which of the following chemicals are used as dispersive agent for hydrometer analysis? Hydrogen chloride, sulfuric acid, sodium hexametaphosphate, and sodium hydroxide. So in case of dispersive agent, you can eliminate the options A and B, because HCl and sulfuric acids are they are essentially acids. And one more thing is, a dispersive agent, most of the dispersive agent contains sodium, and their corresponding salts, those which are sodium salts, are very suitable in acting as dispersive agents, right? So because of its cation exchange capacity. So, and sodium hydroxide is not a salt of sodium, but sodium hexametaphosphate is a salt. So the right option is very commonly
Sir,
used dispersive agents in case of hydrometer analysis is sodium hexametaphosphate.
can you share the screen, sir?
Okay, my screen is not visible. Okay.
No, sir. No, sir.
Sorry. Hope it is visible now.
Yes, sir. Now it's
Yeah. So this is hexametaphosphate. Sodium salts are usually preferred as dispersive agents, and in our applications, most commonly used dispersive agent is sodium hexametaphosphate. So coming to the next question, laboratory sieve analysis was performed on a soil sample using a complete set of IS standard sieves. Out of 500 grams of soil used in the test, 200 grams was retained on 600 micron sieve, 250 gram was retained on IS 500 micron sieve, and remaining 50 grams was retained on IS 425 micron sieve. So compute the effective size and coefficient of uniformity. So total weight is 500 grams and 600 microns. Now let us prepare a small table. Size, percentage, percentage, sorry, weight retained, percentage retention, and percentage finer, right? So first is 600 micron sieve, second is 500 microns, third is 425 microns. So here weight retained is 200 grams, let it be grams here, and 250 was retained here, and 50 was retained in this, right? So the percentage retained here will be 200 by 500. So 200 by 500 will be 40%, and here it will be 250 by
50%.
500, which is 50%, and this is 50 by 500, which is 10%, right? Now percentage finer will be 60%, 50%, 10%, right? Now the first question is effective sieve size. Effective sieve size in micrometers. So effective sieve size is size where 10% is passing through, which is defined as D10, right? Or effective diameter also you can say. Instead of sieve size, it will be effective size. So corresponding to 10%, we have 425 microns. So that is the effective size, 425 microns, right? Now
Excuse
coefficient
me,
of
sir.
yeah, yes.
I think you have not made cumulative percentage retained.
Cumulative percentage, it will come to, this is 90 it will come. This will come to 90.
Then percentage final will change now, sir.
No, here the and the remaining 50 grams was retained on IS 425 micron safe. Compute. Uh,
Percentage retained is correct only. Percentage finer will be small error, I think. In between cumulative percentage retained is required.
yeah. Actually, this question is slightly. This was
No, no.
yeah. So this was in earlier question. So it was asked in earlier assignments, I think. So this I will check it once. Okay.
Okay, sir.
Uh, so then continuously you can find D60 by D10 also. So
Yes,
the
sir.
notion here is to understand the effective size is defined as D10 and coefficient of uniformity is D60 by D10. So that is the understanding that we need to take. And as you mentioned rightly, so it should be cumulative finer. Yeah. So I will check it and modify it accordingly.
Okay, sir.
So coming to the last question, so it is one of the tricky or it is one of the most commonly asked questions to confuse the students and learn this one. So an embankment fill needs 700,000 meter cube of soil with a voids ratio of 0.7. There are two burrow pits X and Y from where the required soil can be taken and transported to the site. So the burrow pit details are given and their voids ratio are given and corresponding the transportation cost is also given. Now we need to calculate if we choose burrow pit X, what will be the transportation cost? That is total cost and transportation cost for the same activity from pit Y. So now we have to clearly demarcate this is X, this is Y, and this is burrow pit. Sorry, this is the embankment or fill. So its total volume is 700,000 meter cube and its voids ratio is 0.7. This is the target which we need to achieve. Same case for in situ voids ratio of X is 0.75 and for Y is 1.65. Now we need, in order to calculate transportation cost, we know per unit volume what is the cost. We need to understand what is the total volume to be borrowed from here, and in case of Y, what is the total volume to be borrowed from here. So here, what is the parameter which does not change in all the three cases? Consider the soil properties, grain properties of X and Y are same, the size and everything. So these are ideal, these are two preferred materials of equal characteristics, but their state of compaction is different, so that its voids ratio is different. So the only thing which remains constant is which parameter?
Volume of the solids.
Yes. So volume of solids is constant and how can we retrieve the volume of solids? So we have total volume here and voids ratio for fill. So that can be used to back compute volume of solids and further that can be used to calculate the total amount of volume of X and Y. So in this case, first E is defined as volume of voids by volume of solids. So volume of voids can be written as total volume minus volume of solids by volume of solids. Now we need volume of solids. So here E is 0.7. Total volume is 700,000 minus Vs by Vs. What is the volume of solids which we get? So 700,000 divided by 1.7.
1.7.
700,
411.
1.7, which gives 4
411 point
1,300 and see sorry
764.
764.
64.
Yeah, 764 meter cube, right? So this is the volume of solids. Now we know E1, Ex and Ey. Now we can find out easily the total volume of the soil that needs to be burrowed, which exist at 0.75 and 1.65 respectively. So the total volume, so in case of, if you consider Ex is equal to 0, that is 0.75 is equal to total volume minus 4,11,764 divided by 4,11,764. How much you are getting? This is Vx. And Vy. Vx, how much we are getting? So it will be 0.75 multiplied by 4,11,764
720.
plus 4,11,764. 720,587 meter cube, right? So similarly for Vy, what you get? For that we can calculate 1.65 equal to V minus four. So what is Vy? 10 lakh 4,11,764 into 1.65 plus 4,11,764. You will get 10 lakh 91,175 approximately meter cube. So we know Vx. So the transportation cost is Vx into 20, which gives 720,587 into 20. which gives approximately 14, 4, 11, 740 rupees. And in case of this one, Vy into 15. Vy is 10, 91, 175 into 15. You get 6, 16, 367, 625 rupees separately, and this one is cheaper. Right? Hope it is clear, right? Sorry, there was a small internet outage. Am I audible now?
Yes, sir.
So till which you have followed?
Only Vy.
Okay, just a minute. I will share the screen. So you have calculated Vy, right?
Yes, sir.
So the next step is it comes to around 10 lakh 91,175.
No, sir.
Vy is, so Ey is 1.65,
Hmm.
right?
Yes, sir.
Now in order to calculate the cost, you know Vx and multiply it by 20 and Vy, and it gets multiplied by 15 and you get these values. So that gives you the cost. So eventually if we compare these two, so transporting it from first, that is X, Boropit X is relatively cheaper. So this is one of the practical applications of where the weight volume relationships of soil come into picture. So with this, am I clear?
Yes, sir.
So with this, we will conclude this session for this week. So this, as a concluding remarks, so this session will be conducted every Saturday 5 to 7 p.m. So I encourage all the learners and the interested learners to join and try to get familiarized with the subject as well as concepts, so that it will be useful for you in your future endeavors. Thank you.
Thank you, sir.
Thank you. I am closing the meeting, so we will meet next week.
Yes, sir.